Hello physicists, welcome to our March 3rd edition of physics. We are well into our redescription of problems using energy. And on Friday we started this quest where instead of just talking about forces and acceleration, we started thinking about things in terms of kinetic energy and work. And we said we know what the kinetic energy is, 1/2 mv squared. How do you do work on an object? Well, you push on it over some distance. And if you push on it over some distance, it will go faster. And when it's going faster, we say now it has a larger kinetic energy. So we're just learning how to redescribe these problems in terms of this new quantity we call energy, which, believe me, it's going to have dividends later off. This will pay off. And in this simple type of problem, which it's not going to let us do anything we couldn't have done before just with F equals ma, but it will let us set up problems. And today we're going to kind of kick the, if we're hanging onto a rope, we're going to kick out the stool from below us and we'll start climbing, because now we can do problems where we're just going to be using energy and we don't have to worry so much about forces. Okay, so all the force stuff, I'm not saying it's wrong. I'm just saying you want to have a way to do problems where you don't have to specify all of the forces. You just want to be able to write down the energies and get out an answer. Okay, so that's what we're going to be doing today. Now, just to make sure that we're not forgetting the stuff about force, let's take a look at one homework problem. Okay, I promise we won't spend our whole time on it. We're just going to do one little homework problem, thinking about forces, acceleration, work, all that. Okay, so here's one that perhaps you've already done. It's on the first page of your new homework that's due this coming Monday. It says a 3-kilogram body is at rest on a frictionless horizontal air track. Okay, so we know the just a sec. You get to see all my messy research habits. Okay, so we've got our mass, which is 3 kilograms, and in any case, we have a stroboscopic graph. That means that you've got like a strobe light that goes boop, boop, boop every half of a second, and we can see where the object is at each one of these moments. Okay, and it asks how much work is done on the body by the applied force between t equals 0 and t equals 2 seconds. Okay, well, we know that work is going to be force times distance. In this case, we don't. The force presumably is going to be in the same direction as this displacement, so the cosine of theta term is just going to be 1. And additionally, we know that this object's F is going to be equal to m times a. So how could I find out what the acceleration is? Well, if I'm just experiencing a constant force, I would expect this sort of thing to be true. This is my constant acceleration motion, the kind of the key equation of it. Now, if I start out at a position of x equals 0, I can forget about that. I start out at rest, which means that my initial velocity is 0, so I can forget about this term. And I know where I am at 1 second, so I can just say x at 1 second equals 1/2 a times 1 second squared. So x at 1 second is 0.2 meters equals 1/2 a times 1 second squared. Okay, so I can then find out what my a is 0.4 meters per second squared. Okay, once I know what my A is, it's going to be easy to find my force because I'm just going to take 3 times 0.4, 1.2 newtons. And then to find my work, it's just going to be that force times the displacement. So over the 2 seconds, I'm getting a displacement of 0.8 meters. I know what my acceleration is, I know what my mass is, and I stick in my numbers, and I should be done. Should get a number in terms of joules, Newton meters. Okay, now today, as I said, that problem is in our old style. The old style has us thinking about forces, and when we push on an object, it adds work and increases the energy. Now, what we're going to talk about today are systems with conservative forces. And I don't want you to don't think that I'm doing politics here. But conservative here means you're conserving something. The amount of energy that you start out is the same at the beginning of the story and the end of the story. That's what it means to be conservative. It means you don't let anything in or out of your system. So if you have 3 objects, for instance, and one of your objects has all the energy at the beginning, and it pushes on another object, by Newton's third law, the forces on them have to be pushing on each other. This object can lose some energy if this object gains. Okay, so you can trade energy around between different parts of your system, but in a conservative system, you can't have energy leaving or coming in. Okay, and we'll relax that a little bit in a second, but this idea that you can have a system where all of the energy is just traded around in the elements of the system is really helpful to doing problems that would be hard otherwise. Okay, and just to make a couple of notes, if you have this sort of system, one nice thing about it is that, let's say I have gravitational energy, moving the way that I add in gravitational energy is by moving up. Okay, so now my pen has more gravitational energy than it had down here. But it doesn't matter whether I move it like this or if I just move it straight up. The path is not that important. So we call this the path independence of conservative forces. And it's also interesting that the key element in a conservative system is that if you do work, the kinds of work that are being done by that closed system, for instance, if I throw my pen up, it will get slower, and as it goes up, the energy is being traded from the kinetic energy into potential energy, and then it comes down, and the energy is traded from potential energy back to kinetic energy. And over that whole circle, the amount of work being done is 0. And so this is something to think about. On the way up, the gravitational force is doing negative work. On the way down, the gravitational force is doing positive work. The net work was 0. Now, in this course, we're going to have just a couple of types of energy that we care about. In real life, there are more. For instance, there's the mass energy of the nucleus, or the chemical energy of a molecular bond, that sort of thing. But the point of this course is just to give you a framework to understand how these sorts of problems can be thought about. And the way that we think about our energy is that it's just stored work, essentially. So for instance, for kinetic energy, we say that's 1/2 mv squared, okay? And we just cooked up that definition so that the work energy theorem would make sense. Now, for gravitational potential energy, the force of gravity is m times g. And if you integrate that over some distance, so I guess I don't know if I should say this, if it'll be more confusing than it's helpful. But essentially what you're doing in each one of these cases is that the energy is the integral over the, let me put it in there. You have minus the integral from x initial to x final of the force. And so what this is saying is this is essentially negative work. You put work into the object, and then you say if whatever work is, whatever energy, whatever kinetic energy leaves the object, in a conservative system, that energy is gained in terms of the potential energy. So for instance, in the gravitational potential energy, okay, your force is going to, in the y direction, it's going to be minus mg, right? And then your potential energy, you can find by going from like 0 to some height. You start out at y equals 0 to y equals h. And then you go minus mg, and then you put a minus sign on there to cancel it out, basically, and you get m times g times h. Okay? Same thing with elastic energy. Okay, so the F is going to be minus kx. And so, for instance, if you wanted to stretch your spring out, you'd go from 0 to x, you'd go minus a minus kx dx, and then that would be your u, and so your u there is going to be 1/2 kx squared. And so the idea there is that if there's work being done on the object, okay, if there's a work being done on the object, it can be gotten back out. So this is negative work as the object goes up and it's slowing down, but that can be that negative work can be gotten back out and turned back into kinetic energy if it drops. Same thing here. If you start out with a spring and you stretch it out to some further distance, x, you can get that energy back out in the form of kinetic energy if you just let the spring go. The ball will fall back and it'll be turned back into kinetic energy. And so if we ignore our heat losses, the idea is that we can add up all of the kinetic energy plus all of the potential energy, and that will remain as a constant. It'll be conserved. It'll be equal to the kinetic energy plus all of the types of mechanical energy throughout the whole system. So a good example of this is in terms of our pendulum. So let's say, for instance, that we lift up our pendulum and we just let it go. It'll start swinging down, and as it swings, it'll gain kinetic energy and it will be losing potential energy. The potential energy is the mg times h. So just to draw it a little bit more clearly, the h that we're talking about is this h. Okay? And the v that we're talking about is however fast it's going. So it's got its maximum speed right there. It has v equals 0 when it turns around. And so what you're seeing here is that in the middle it has all kinetic energy. Then as it begins to slow down, some of that kinetic energy gets transferred into gravitational potential energy. And then as it turns around, all of its energy is potential energy. And it just keeps going through this cycle as the pendulum goes back and forth and back and forth. Now, of course, you might say to yourself, I don't think that that's really happening. I don't think that there's anything called energy that's sitting inside of that pendulum that happens to be sloshing back and forth like some liquid. It's just being acted on by forces, and it pushes it back and forth. And I'm very sympathetic to that view. But as I'm trying to push to you today, it's not that you have to believe in energy. It's that it's a useful way of talking about a system that helps you to take some shortcuts when you set up problems. So let's give ourselves another easy example. Okay, you are investigating the safety of a playground slide. You're very interested in finding out what the maximum speed will be of children sliding on it when the conditions make it very slippery. So we're going to assume it's basically frictionless. The height of the slide is 2.5 meters. What is the maximum speed of a child if she starts from rest at the top? Okay. Now, the way that we have done this problem, we could, in fact, do this just with forces. How would we do it? Well, we would find out the component of the gravitational force acting in along this direction, and then we could go ahead and multiply that and do a force times distance and find out how much work was done. Once we find out how much work was done, we could go ahead then and find the change in kinetic energy. Okay? So that's the old way of doing it. What's the new way? Well, the new way is just to say, what kind of energy do we have at the beginning? What kind of energy do we have at the end? If we add up all the types of energy that we have at the beginning, it should equal the amount of energy that we have at the end, because we're just conserving energy, and before energy equals the after energy. So what kind of energy do we have at the beginning? Well, it's not moving, so we don't have any kinetic energy. It is up at a height, so we can just say that the energy before is whatever potential energy from gravity we have. At the end, we just have the kinetic energy. Okay, so all we have to do here is say m times g times h, that's our gravitational potential energy, equals 1/2 mv squared. Easy as that. And I notice that the masses cancel out. I can go ahead and multiply both sides by 2, take the square root, and find that v equals square root of 2gh. And you find out that you should end up with something like 2 times 9.8 newtons per kilogram. Or I think it's actually easier to write meters per second squared there, times 2.5 meters. Okay, now, an interesting point to realize here is if I have a very steep slide, or if I have a very shallow slide, somehow I'm getting the same final speed out of both. How does that work? Well, remember what I said at the beginning of setting up this problem in thinking about it the old way. In this case, you're going to have a big force of gravity. Almost all of the gravitational force is going to lie along the direction of that plane. But you have a short distance. Remember, work equals force times the distance. So if you have a bigger force and a shorter distance, that can give you the same amount of work as a smaller force and a farther distance. Okay, so that's what's happening here. This h is the same in both cases, and this energy formalism allows you to kind of sidestep some of those issues and cut straight from the beginning of the problem to the end of the problem. Let's see how this works in a homework example. Here's a homework example. You have a 2-gram ice flake. So the mass is 0.002 kilograms. Is released from the edge of a hemispherical bowl whose radius is 22 meters. So that H at the beginning is, or 22 centimeters, 0.22 meters. The flake bowl contact is frictionless. A asks, how much work is done on the flake by the gravitational force during the flake's descent to the bottom of the bowl? Well, let's think about this in terms of energy. At the beginning, this flake just has some gravitational energy. At the end, when it's at the bottom of the bowl, it will just have, for instance, kinetic energy. How does that energy get transferred from gravitational energy to kinetic energy? Well, the gravitational field does work on the ice flake, right? It's going down this way. There's some component of that gravitational force that's in the direction of its motion. And so, for part A, how much work is done? Remember your kinetic, if your kinetic energy is just all coming from your gravitational energy, your K final is K initial plus the amount of work. That's your work energy theorem. If your initial kinetic energy is 0, the amount of work being done by that just has to be equal to your mgh, right? Because that's your initial gravitational potential energy. This problem's a little annoying because it just asks the same thing a bunch of times. What is the change in potential energy of the flake Earth system during the descent? Well, if it's going from a higher potential energy to a lower potential energy, it's just going to be minus mgh. Okay, because at the beginning, your UG at the top is going to be equal to mgh. Your UG at the bottom would be mg times 0, so that's 0. So your delta G, or your delta U, is going to be 0, that's at the bottom, minus mgh. So that's why you get a negative for the second part. Okay, CS, if the potential energy is taken to be 0 at the bottom of the bowl, what is its value when the flake is released? Okay, you're back here, mgh. D, if instead the potential energy is taken to be 0 at the release point, what is its value when the flake reaches the bottom at the bowl? So here they are making an important point that you never really measure the energy full stop. You measure changes in energy. So in this case, if this were considered to be a 0 energy, that's actually fine because you would just have a negative energy at the bottom of the bowl. So this would be minus mgh. In that case, your kinetic energy would still be positive to keep this total energy 0, if you see what I mean. Okay, and then part E asks, if the mass of the flake were doubled, would the magnitudes of the answers A to D increase, decrease, remain the same? They would remain the same. I will let you write out a couple of equations and see if you can convince yourself of that. Okay, now, conservative forces just require you to think about energy being shuffled around between objects within your system. So, like from the kinetic energy to the gravitational field, for instance, or from the kinetic energy to the spring, or from the spring to kinetic energy, or from spring to gravitational field, or however you like to think about that. Now, it can be still convenient to sometimes think about adding energy to a system by pushing on some part of the system, or taking out some energy from the system when you have you have some of the energy lost as heat, for instance. So we can always do that. We don't have a totally conservative system anymore. Then we're acting with some external forces to change that system energy. And so this seems a little bit confusing, but in practice, it's pretty simple. And I think just doing a simple problem with it is going to allow you to see how this works. So let's look at a homework problem that I gave you. That's a pretty straightforward situation. You got this adorable 25 kilogram bear, and it is sliding down a tree. Okay, so I'm going to represent that bear as a dot. And there's some force of gravity going down, and he's clawing and providing some force of friction going up. Okay? And so essentially that force of friction is taking energy out of the system. If he was just dropping if he just jumped off the tree and allowed himself to drop, all of his gravitational potential energy would be converted into kinetic energy. But in this case, some of that is being lost due to friction. So let's just look how it is. We're going to, a 25 kilogram bear slides from rest 12 meters. So this height is 12 meters. Moving with a speed of 5.6 meters per second when he reaches the ground. Okay, so he's from rest, so this V initial is 0 meters per second. The V final is going to be 5.6 meters per second. And they ask, what change occurs in the gravitational potential energy of the bare Earth system during the slide? Okay, so if I'm going to look for a change, I'm going to be looking at the U final minus the U initial. Well, let's say that we call this height 0, and then I'm going to have minus mgh. Okay, so that's one thing. Now, B asks, what is the kinetic energy of the bear just before hitting the ground? Well, he's lost potential energy, and he's gained this much energy as kinetic energy. So what you would write down essentially is something like this. The gravitational energy at the beginning equals the kinetic energy at the end minus whatever energy has been lost through heat. Now, K you can of course just find because you know the mass of the bear, the final K. You know the mass of the bear, you know the speed of the bear at the end, so you can just calculate that. For C, using this, because you know this is mgh, this is 1/2 mv squared, v final squared, you can go ahead and also find that thermal energy. But that thermal energy is the result of frictional work. Negative work, of course, that's why we have a minus sign there, but work nonetheless. So that minus E thermal, or let's just take it as E thermal, is going to equal the frictional force times the distance. Okay? And it's negative force, it's a negative work because it's causing him to slow down. It's directed opposite the direction of motion. It's at 180 degrees from the direction that he's moving. So in this case, you know the displacement is going to be 12 meters. You want to find this. and this E thermal you're going to get from over there. Okay, so the problem is not too bad. It's just a little, you've got to do a couple steps of thinking to set it up. Okay, so I'm going to let you try some of these problems. Please, if you have questions on them, let me know, and I will try to go over them on Friday, either in class or in the video, hopefully both. All right, now, last time you might remember I did not have time to get to the power questions at the end. Power is not, it's not a hard idea. It's just if you have work being done over a certain amount of time, the way that you quantify that is with power. So power is in watts, which is a unit of joules per second. And if you want the average power, you just take however much work you're dumping into the system divided by however much time it took you to dump that. If you want the instantaneous power, you can imagine making that time interval very short and thinking about it in those terms. However, if you start thinking about it in those terms, the instantaneous power is d dt of the work being done. Well, let's say that you do it like this. You do d dt of the force times the displacement times cosine of theta. Okay. Now this force, we take that to be constant. Let's just say it's constant for a second. It's instantaneously constant. And then in those terms, for a constant force, we would find that this would be F d, and then just to make it look a little more familiar, I'm going to put an x there instead of a d. dx dt times cosine. And so essentially what you have here, this is the velocity. Okay, so what you would have is the power is F, the force, dotted with V. So for instance, this would be Fx Vx plus Fy Vy if you were doing a two-dimensional force. Or you could just have this as F times V times the cosine of the theta between the velocity vector and the force vector. Okay. I don't want this to seem too intimidating, though. It's just the same ideas. It's just that now instead of just thinking about it as a force, we're thinking about how much work we're putting in. And instead of just thinking about the work, we're thinking about work per unit time. And because pushing on an object in the direction of its motion could give you positive work, pushing against the direction of its motion could give you negative work, you can also have positive and negative power. Positive power means you're adding energy into the system per unit time. Negative power means you're taking energy out of the system per unit time. So there's nothing super new about it. It's just a little tweak on top of what we've already done. So here's an example of a power problem. While you sleep, your body is using energy at a rate of 77 watts. Okay, so the energy that it's using over time is 77 joules per second. How many food calories are used during an 8-hour period? Okay, so if you want to find the energy, it would be this power multiplied by time. Okay, so you'd have 77 joules per second times 8 hours, and we would have to put that in terms of, okay, I guess 1 hour is 60 minutes times 60 seconds, so 60 squared seconds. Seconds cancel out, hours cancel out. We're left with an answer in joules, and it says It wants us to give an answer in food calories. Calorie is just another unit of energy like a joule. And we can then go ahead and convert from joules to calories. 4186 joules per 1 calorie. Now, it's perhaps a little surprising to you how many joules you get out of 1 calorie. And it's an interesting fun fact that, in fact, if you have a cookie, that has more calories, it has more stored chemical energy than the same mass of TNT, the stuff that you use for dynamite. And if you think about it, it kind of makes sense, because if you eat a cookie, you take that energy and you use sledgehammers on a car, for instance, you can do a lot of damage to the car. So the difference, of course, is that TNT can release its energy all in a very brief amount of time. So that's why they use TNT and not cookies for dynamite, despite the fact that the energy density of cookies is higher. Okay, here's a quick homework on power. This is the last problem we'll do today. It says a force of 5 newtons acts on a 15 kilogram body initially at rest. So we've got a force, 5 newtons. We have a mass, 15 kilograms. It says compute the work done by the force in the first second, the second second, and the third second, and the instantaneous power due to the force at the end of the third second. Well, I got to use my physics brain now. If I know a mass and I know a force, the thing that's humming in my head is the thing that I have on my invisible knuckle tattoo, F equals ma. So, F equals ma, 5 newtons equals 15 kilograms times a. So this mass is now accelerating at, I guess, 0.33 meters per second squared. Okay, so it's getting faster and faster and faster. And if I want to find out how far the object has gone in the first second, the second second, and the third second, I can just use x minus x naught, this my favorite of the acceleration v naught t plus 1/2 a naught t squared. Let's assume that I'm starting at rest, because the problem tells me that, and let's assume that our initial position is 0. Okay, so if I want to find out my displacement at t equals 1, I would just go 1/2 a naught 1, this being my a naught 1 second squared. If I want to find out how far I'm going to go, you see where this is going. After 2 seconds or after 3 seconds. Okay. Now, if I want to find my force, if I want to find out the work that has been done on this object, I would just go the force, which I know, times the displacement. Okay. And then it asks, the last one asks me the instantaneous power due to the force. So that's how much energy is being added per second at that immediate time. And this is sort of easy because it's just F times V. And of course, you can find out what V is using the derivative of this equation. The V equals A naught times T. So at the end of the third second, you're going to have some speed which is 3 times that. So not to give anything away, but I believe it's going to be 1 meter per second. And then times the force, 5 newtons. So there is something interesting about this, which is that if you can continue to push on something with 5 newtons as it goes faster and faster and faster, you're going to end up doing more and more and more work. And so that's something that takes a little thinking to be able to convince yourself that that's right, but it is in fact correct. Okay, so what have we learned today? When a system is isolated, the energy within it is constant, but can be shifted among the objects and among the various energy types. That's what we mean by conservative forces. External forces can be non-conservative, which allows these isolated systems to gain energy or lose energy. Okay. And then finally, the idea of power lets us quantify how much energy is dumped into a system over time. All right. On Friday, we're going to pick up a couple of odds and ends from this unit, but today we had a lot of information that was presented in this video. It should be enough to get you at least started on every problem that's due on your homework set on Monday. So please take the time to try to make progress on it so you can ask questions. Yeah. So this Friday, we'll take a quiz. We'll finish up some odds and ends. Next week, Monday and Wednesday, we'll be reviewing stuff from this unit. Next week, Friday, we will take our exam. Okay, so thank you for watching, and have a great day.